Okay, so this is our test 1 review session. Let me zoom that sucker in. There we go. And I'm going to just kind of talk a little bit about what's going to be on the test and how it's going to look. I think most of the people in this course have had me before in another class, so you've probably seen one of my tests before. So just to make sure, though, if there's, I can't remember if there's any random people, but just to make sure, we're going to make sure everybody knows what's going on. I generally have several sections. So that's all right. All right, so the first section is almost always some kind of a matching section. And I can tell you in the math history, I generally have like 2 or 3 different categories. And I think I mentioned this early on in the semester. There's normally like mathematicians, matching, civilizations. So knowing, you know, which one was used metal and required proofs and stuff like that, that would be the Greeks, right? Okay, so civilizations and artifacts. And at some point there might be a map question, which would also be half points. And on the map questions, those would be the cities. So those are kind of the 4 things you've been supposed to be keeping track of as we go along. So hopefully you have seen those. We don't have a ton of mathematicians that we know by name at this point. Starting with Thales, going through, I think I'm gonna, like I was looking at the material. I know that last week I put up videos into Diophantus. But there's the, did y'all get to do Diophantine equations yet? Have y'all done that homework? Okay. So I was about to say, I think I'm going to actually cut the test at Archimedes. So if you have done all the stuff through Euclid, all the stuff through Archimedes, for instance, make sure that you know material through Archimedes, which just means I'll throw Diophantus on the next one, but I said in the online on B2L that I would include through everything, and Diophantus is in the stuff from last week, but he's kind of an unusual guy. He's a Greek guy, but he's in the Roman period, and he's in Alexandria, which is Egypt, so he's kind of got a little bit of everything going on. So I'll hold him off a little bit. So let's say through Archimedes. And so you need to know the Eureka story about Archimedes. If you haven't watched that video yet, the Nova video, where he's running through the streets naked, make sure you've done that. Okay. That was on last week's D2L, so there's a video up there. And make sure you know Euclid's favorite quote, give that guy a coin if he must learn or must profit from what he learns. So that's in there. I think that was on the quiz for Euclid. So, you know, if it makes it to the quiz, it's probably pretty sure that it's going to make it into a test question. So look through that, but I'll hold off on Diophantus. So matching and maps, both worth half points. And then we have true, false, which are worth 3 points, but they're Webster true falses, which means that you have to give a reason for what your answer is. So if you just say true or false, you're just going to get a point. Okay. If you say true or false and you get it correct, you might get 2 points, but you're not getting full points unless you tell me why or why not. So make sure of that. Alexis, you have a question?
On the quizzes, is there any way you can open it so we can look and see what we got wrong?
If I can open what?
Like the quizzes to where we can see what we got right and what we got wrong.
I don't know how to do that, actually. I know that you're supposed to be able to do it. I'll look at it, but if there's a specific one you want to know about, I can for sure open it and I can see what you did right or wrong and let you know. But I'll try to figure that out. I'm sorry. I know you can do it. I just haven't figured it out yet how to do it. Okay, so true, false are 3 points. Multiple choice are 3 points. And again, for multiple choice, make sure that you follow directions, because sometimes they say select all the things that are correct, or select everything that is true except the one that's not, or find the one that's not true, or whatever. So just read the directions on that and make sure. You don't have to give reasons for multiple choice, but sometimes there are 2 or 3 correct answers. All right, and then there's always short answers, which are worth 4 points. And then there's always calculation problems, which often include proofs, which are 5 points. I Zoomed with somebody from this class yesterday, and we did one of the proof questions out of the homework. And it was a really long question by the time we got finished with it. And she said, is this kind of thing the kind of proof that's going to be on the test? And the answer is actually no. So remember that on homework, that's your opportunity to practice, right? And that's the opportunity where you can look stuff up and ask questions and things like that. So sometimes the homework questions are just a little bit tougher than what I would ask on a quiz or on a test question. So for sure, for proofs, no Garfield's proof, right, of the Pythagorean theorem. Make sure you can do that proof. I'll provide the picture, but you can work it out. Make sure that you can do some of the more identity kinds of proofs that are like trig problems, where I say, prove that this formula is true, like for the splitting identity, or the one that's 2 over 3k, that formula where I say prove that this is true. So, and that's just basically manipulating one side or the other and making sure they look like each other. And then if I have one from the more recent homework, which would be like page 75, I might be doing something where I say, okay, can they manipulate this a little bit? So if you don't remember the proof from, I don't remember the exact thing, but say it had something like this. The proof from page 75, part of it looked like that. And there might have been a plus n plus 1 or something like that. So the problem with this proof was that there are 2 different variables, right? So over here I have n's and over here I have triangular numbers. And so to be able to work with it and manipulate it, you have to do something to substitute out that triangular number, right? But if you've watched the videos and you've done all the work, you should know, you should have seen by now lots of times Gauss's formula, right? So that's what. Instead of triangular numbers, he figured out you could do n over 2 times n plus 1, right? Okay, so add the first, add the last, the nth term and the first, and then multiply that by the number of terms you have, divide by 2 because you're pairing them up, right? So here's where we pair them up, here's where we add the first and the last. So to substitute that in, and then you would have something with just one variable, right? And now you can work with that algebraically. So I might ask that you do something kind of simple like that with a substitution type thing, but it wouldn't be one of the really long proofs like was on page 75. I think that was 14. Ended up being pretty long. So that's the background of what the test looks like. Yay. What questions do y'all have? Anything about material?
Are we going to have to be drawing out Babylonian inscription numbers?
Babylonian, yes. So, well, yes for both. So I will give you the chart that I handed out in class that has the, so included in your test is the table with the 2 over n table and the Egyptian hieroglyphics. So that will be with you. So you will be able to just look at that and work on it. So there could be some numbers where I say, here's a base 10 number, write it in Egyptian hieroglyphics, and all you have to do is reference the chart and be able to write them out. So you might have to draw those. But also, so that'll be given. But for you, you will need to know the Babylonian numbers. I'm not giving these. I feel like it's pretty easy for you to remember. They had basically 3 characters, right? One was what? How'd they draw that? Yeah, it's like a stick. Theirs actually ends up looking, the stylized version is like that because they're using that stylus and dragging it down, so it looks kind of triangular, but you can just do a 1, and I'm okay with that. Okay, a 10 was what? Yep, I call it the Pac-Man. Theirs look something like that, but you're welcome to use the less than sign, okay? Because that's just makes our life easier. And the third one was for 0. And what about that guy?
Space, right?
Well, the early days, they just left extra space, but they actually around 300. Yeah, so around 300 BC, they would just use the 2 triangles, right? They go dot dot with the stylus. There's also that slicey sideways long triangle. If you want to do that, there would be 2 of those going, but most people use the triangle on top of the triangle. So those are the only 3 things that, for my purposes, I feel like you need to memorize for the test. Formulas such as the splitting identity will be somewhere on your test. If you need the formula for the area of the trapezoid, it'll be somewhere on the test, or I'll put it on the board. I don't care. You should probably know the area of a triangle, but if you don't, I'll put it up on the board. I'm not really stressed about those kinds of things. This is not for me about memorizing that. If you're going to spend your time memorizing stuff in this class, spend your time memorizing which mathematician wrote which book, right? Because that's going to pay off for you more. I think that people where they struggle on these tests is it tends to be it's about 50% history and about 50% math. And normally in this class, everybody zooms through the math. Like that's not really the problem. The math isn't an issue because the math's not too terribly difficult in here, right? But it's the history that tends to grab us. So I think in week 7 in D2L, I put up a list of all the primary mathematicians. I think that was last week I put that up. Or it might be in week 8. I don't remember. But somewhere I put a list of mathematicians. So if that helps you to study, feel free to use it. I also put up a clean world map on there. So 2 things I put up. I think it was last week, but it might be this week's material. Clean world map, if you need that. There's probably a map question on this test. And I think it says primary mathematicians in this class so far or something like that. So in that particular thing, I have kind of a grid laid out where it's like, okay, here's Thales. Here's his motto, which remember Thales' motto was, he's the first. Know thyself. Yes, that was his motto. So remember, he was the first guy we know, and he's this Greek philosopher, right? He's one of the 7 sages. So know thyself. It's very, philosophy based or whatever. So that's his motto. What else do I have in there? If there's any dates that you do not need to memorize dates. Do not worry about dates. That's just so that you have an idea where things fall. What else do I have on that stinking list? If they have any books that they wrote, like not Thales, we don't know of a book that he wrote, but Euclid clearly wrote the Elements, right? Which is like 13 books, right? Not just 1, but so he would have that. What else did I put on there? I might have something like what's their contribution to math or something like that, just so you can process it. Didn't I send that? I didn't put that online. Did I put one online? I can send it out if that helps. Did I? Nobody knows. I don't know if this thing will let me in. I have my thing with me. I can get in here. Oh, list of primary mathematicians. It would have been on week 7 because I put them up a week early. I always try, but maybe it's sample questions. Okay, it is there. Is it week 7 or 8? Okay. I might have put it in 8 also. So there are sample questions, guys. And if you want to talk about some of those today, I'm glad to talk about them. I'm like, I think I put it online. But you know, I have been known to not put something up I thought I was putting up. Your audio cut out again, Maria. What is going on with your thing? If you need to log out and log back in, you can. That actually comes in on the Roman videos, so y'all are right there at it. Do we know? Why?
Julius and Augustus Caesar.
She looked very happy about that. Why do you know that?
I took Latin in middle school and high school, and so I learned a lot about like Roman history and the architecture, or like architecture and infrastructure of Roman life, and
That's interesting.
settling in Alexandria and all the different things with that.
Nice. How many years did you have to take that?
I was in the actual class for 4 or 5 years, but I did Latin club in high school for 4 years. So like overall 6 years of material.
Wow, that's crazy. Can you hear now, Maria? Great. All right. So, yeah, so Summer is telling us all about Julius and Augustus Caesar, who were what? Roman emperors, right? So when you look at the original calendar that we had been working with so far until the Roman period, there were, I don't remember how many months, but 10, yeah, that makes sense. So whenever we did some adjustments to the calendar to make it more realistic, so that when you have the solstice one year, it falls about the same time every year. You don't want it to be drifting one way or the other. So they made adjustments to it. When they did, they made 12 months. So July and August, those are your two new months. Good, good. It should be in the video on Romans, which I think was on week 7. So that was probably Thursday stuff. You're probably just not there yet. What else you got?
And you said the guy whose name starts with a T. You're gonna wait for him.
Yeah, I'll hold off Diophantus. He'll be on test 2.
And I'm guessing question 20 might be answered by the Thursday video. And then the African Middle Eastern European areas of the world from the time of the Christian crusade to the line of the Islamic armies through the time of the Indian.
Okay, so which number is that? Is about the Arab period. So that'll be on test 2. Good question.
And then 23 is be able to compare the square of algebraically and geometrically is the way that somebody whose name I cannot pronounce did in his book Algebra to practice. You can use
Okay. Good. So 23 is about Al-Khwarizmi.
Sure.
You'll be able to pronounce his name before long. And he's an Arab, and we have, I just had to push the material, so we're just not there yet, guys. I stuffed as much as I could into last week and still felt terrible for stuffing too much, I think. So, yeah, so Diophantus in the Arab period, they were on the original sample questions, but they won't be till test 2. What's in 21 and 22? Just okay, Diophantine equations. So basically 20 through 23.
And number 19 says discuss Archimedes. So that would be like the
Okay.
last question we have.
Good. So you will have to discuss Archimedes. All right, so 20 through 23, it looks like all of those, just hold on to them because you're still going to have to know them, just not yet. Good questions. All right, what else you want to talk about on the review or anything you got going?
Would you mind working like a sample first, like the triangular numbers?
Which one do you got?
Anything?
Is there not one on the sample problems?
It's
I'm sorry.
understand triangular and square numbers as well as other formulas are developed.
Let's do square numbers because that's where we were in the content in class physically whenever we got dumped. And it's on the videos, but I want to make sure you're really good with them. So let's just talk about that real quickly. We had done a lot with triangular numbers, I feel like, before we left. But square numbers are numbers that you can make dots into squares. So not rectangles, be careful about that. So like I said, for all of them, the number 1, we can put 1 square around 1 dot, right? Okay, so 1 is almost always the initial guy for all of these series or sequences. Okay, so what's the next square number? How can I do dots? Yeah, 4 is the next square number. So how can I do dots to represent the number 4? A 2 by 2. And that is a square, right? And what's the next square number? 9. So I can do that 3 by 3 in the dots and make a square. And let's do one more. 16, right? So that should be 4 by 4. And one of the things that I thought was really interesting whenever I took math history a long time ago was that, you know, the number square numbers, what we call them, and we even do like x squared, like the general formula for this would be y equals x squared, right? And this one's actually weird for us because we know that general formula, we actually don't know the recursive formula. But with the triangular numbers, we knew the recursive formula and we were trying to find the general formula whenever we got cut off, right? So, so Gauss found that for us, thankfully. But so this one, I thought it was really interesting because we called this thing right here x squared. And it came back around to me when we were doing geometry with the Egyptians and stuff like that. The reason why they called them square is because normally they were talking about like plots of land. So they would do a square of land and that kind of thing. And so whenever they would be drawing it out, maybe, I don't know, it looks something like this, but there's a river going through it. Okay, so you can't quite make it meet up. They would say, oh, but if those are the same measurement on both sides, then that makes a square. We just don't quite know. We know how tall this is, but we don't know necessarily how wide that is. So they would just say, oh, that's the unknown, because in the old days, whenever you read this stuff, like from Euclid, by the way, he doesn't write x squared, right? He doesn't have that nice algebraic notation we have nowadays. Instead, he would say some quantity squared, you know, or the square of some quantity or something like that. But that comes from this geometric thing that goes way back to the Egyptians. And I thought that was really cool. It's a neat connection. Where does that square come? Why do we call x with a 2 up in there squared? And that's why. It was really square. Okay, so whenever we look at this, we say, okay, I want this, I've got this general formula. What about a recursive formula? Because sometimes it's nice to see both. And it would be really, really nice if we had the recursive formula and then we could work that out and make it equivalent, prove that it's equivalent to the general formula. That would be great. Okay, so what are we doing here to get from this term, the first term, to the second term? Adding 3. Does everybody agree? So there's actually a picture in one of the books that looks something like this. Here's the first square number, and to get it, I add 3. And then here's the second square number, or the first square number, and here's the second square number right there. There's a 1, a plus 3, and a plus 5 going on there. What's wrong? Oh, thank you. And then to get to the next one, same thing. We can see them embedded in there. 1, plus 3, plus 5, plus 7. Okay. So what are we doing here to get to the next term? If I wanted the very next term, which would be, we know the square number is 25, add 9, right? 16 plus 9 is 25. And if I wanted the very next square number, which is 36, to get from 25 to 36, I add 11. Okay, so we see, what are we doing? Adding odd numbers. Okay, so the question becomes, how can I represent those? Kind of like in the square numbers. 1 plus, plus, plus. Okay, how can I get those represented? 1 plus 3. How can I say 3 is related to, this is the first term. How's 3 related to the second term? Okay, it's plus 2, but would 5 be the third term plus 2? Okay, how am I going to get there? How do I get odd numbers? Let's back up. How do I get odd numbers algebraically speaking? Add 1, right? So I need to start with an even number and then I add 1, okay? So how do I get an even number? Whatever term you're on times 2, that'll automatically give you even, right? Okay, and then the odds is just, and it's actually plus 1 or minus 1, right? So I think in this case, we want to think about, this is the second term. If I did 2 times 2, I'd have a 4. So what would I need to do? Add 1 or subtract 1? Okay, so 2 times 2 minus 1. Does that work here? 2 times 3 minus 1 gives me 5. Yeah. And then, well, I skipped it, but 2 times 4 is 8 minus 1. That gives me the 7. So on and so forth. So if this is the number of the term that I'm on, then here the generic would be 2 times n minus 1. Is that okay? For the nth term, I'm doing 2 times it and then subtract 1. That gives me the odd number that I'm adding. Does that make sense? Okay. And as you work through these, like I took a couple of classes in number theory and discrete math, which are always fun if you're looking for an extra math class. But as you work through those, you figure out things like, oh, if I want to represent an odd number, it's like almost always either 2n plus 1 or 2n minus 1. That's one of those two is the way you represent them. All right, so now let's think about Gauss, because we're looking at that triangular thing. That's what I was asked for. So the first guy plus the last guy. What would that be? 1 plus the last guy here is 2n minus 1. Okay. And we know if we come in evenly on both sides, go up one term and down one term, that those will average out to the same thing. So we don't have to do it over and over again. But if you wanted to, this guy is 3. The one before this would be 2 before this, so it would be minus 3. So it'll add out, okay? But you can check them. What does this add up to? 1 plus 2n minus 1, 2n, right? So each of these pairings is going to be 2n. Does everybody agree? So this guy and this guy, we would have all these pairings that were adding out to be 2n. Well, then what? Okay, so the question then is how many pairs? And actually says, oh, that's always the number of terms you have divided by 2 because we're pairing. Pair means 2s, right? Okay, so now I've got 2n times, I'm going to stick that over a 1. N over 2. 2n times n is 2n squared over 2. We know 2 divided by 2 is 1. Look, it's n squared. Oh my gosh. Surprise. We already knew that was going to be n squared, right? But it's kind of cool to see it fall out for us. Yes. Yeah, we're using Gauss's method. Add the first guy and the last guy, pair them up, and then multiply that by the number of pairs that you have. Okay, that's the Gaussian method. He did that with triangular numbers. What we find is we can attach that basically to all kinds of stuff. We did it here with square numbers. In your homework, you had to do it with cube numbers, right? Same process. And then later, when he was around 17, let me think about that. He found it at 10. I think he had the formula by 15. He had the proof by 17. And I think around 22, he was just fascinated with this once he got on it. I think around 22 or 25, he actually had shown that you can actually use it for skip counting too. Because all the ones we do are consecutive numbers, right? So 1 plus 2 plus 3, or in this case, it's odd numbers, 1 plus 3 plus 5. So he figured out you could do it like every fifth one. So if you had a formula where you added 5 every time, like maybe you started with 3, plus 5 is 8, plus 5 is 13, plus 5 is 18. So if you had something like that, he was like, oh, you can use my formula. So you can use my method, and you just have to adjust, basically, because you're starting at 3 instead of 1, so you have to make an adjustment there, tweak it. And then instead of counting by 1s, you're counting by 5s. Well, here, we actually adjusted for the counting every other number, right? By 2 is what we have here. Because we weren't adding consecutives, we were adding odds. Does that make sense? Okay. So, yeah, so he had done that and figured out you can do it for all kinds of sequences. So if you had something like the one I just mentioned would be like 5n plus 3, right? Start with 3 and then add 5 each time, 5n plus 3. That's your general formula, but you can do it, you can find it using recursive and pairing. So, kind of cool. Did I answer all your questions? We didn't get a chance to talk about all this, so. Sorry, guys. Less airflow, but I can hear. All right. We didn't get a chance to talk about all that stuff, so I hope that you were able to watch videos and do formulas and work proofs and all that, do the homework. Anything else in the review or questions that you have? I know I just closed this in here.
75. Page 75.
Can you just say it again?
I said I have a question about page 75, the homework.
Okay, what you got?
It says prove that any angle inscribed in a semicircle is a right.
Did I find that?
Sounds like a last semester.
That's what I was like. It sounds like geometry question to me.
It's page 75, and you said number 1. It was the first question.
Is number 1? Oh, okay. So it says prove that any any angle. What did it say, Alexis?
Inscribed in a semicircle is a right angle, and then this is sometimes called Thales theorem.
What's the end of it say? I'm sorry.
This is sometimes called Thales theorem.
Thales' theorem, yeah. So you're looking at some very early Greek geometry here. So he was probably the one that worked with it and messed with it. So they're giving him a little bit of credit for having done some of this work. Probably we know that because of his followers telling us. All right, well, that wasn't a question I was expecting, but we can do it. So what's a semicircle look like? Anybody can answer, it doesn't have to be. All right, it's a half of a circle, right? So when you measure it, it's 180 degrees. Everybody agree? Okay, and they're talking about an angle that's inscribed in it. So we have to use a tiny bit of our geometry to say, hey, does it matter, by the way, inscribed angles say that your endpoints and your vertex all are points on the circle, right? Okay. Does it matter if I make my angle over here or if I make my angle over here? That's what they're asking, okay? So what they're saying is, hey, these kind of look like right angles to me. Okay, they're inscribed in the semicircle. So because it says semicircle, that means my endpoints need to be on the diagram or diameter here. That's why I'm putting those guys there. So inscribed in there, and they're saying, hey, are these 90 degrees? Well, what kinds of stuff do we know? Let's give some labeled points. A, B, C, D. I don't need both of those triangles. I could just do one triangle if I want to. If we were in geometry, you'd probably do a 2-column proof, right? But we can talk about paragraph proofs if you want to. I don't care. Yeah, I don't care. Whichever way y'all want to do it. Okay, so Summer has given us the one little number thing that we know, which is that a semicircle is 180 degrees. What about a right angle? What do we know about that number-wise? 90 degrees, right? Okay, so what they're saying is that prove angle, I'm going to pick ACB, his measure is 90 degrees. That's what they want me to work on. This should be like nothing for you guys. You had me for geometry last semester. There's a property that we need to invoke here. What is it? Okay, so there's a property that says that any inscribed angle is half of what? I don't remember the name. It's probably called like the inscribed angle property or something like that. But there's a property that says if an angle, let me give you, is inscribed, its measure is half that of the central angle with the same endpoints. That's what Ashley just told me, right? It's half the measure. So when we see that one, normally it looks something like this. Oh, here's this guy here that's the central angle, and we have some inscribed guy like that. They have the same endpoints, and we would say, oh, ACB is half of AEB, right? Okay, so that's the thing that they're trying to get me to invoke here, okay? But I need to look at this as this diameter right here is a central angle, right? It's just the flat angle or the 180 degree angle, and we would call it AEB just like we would down here. It just looks different because it's on a semicircle. So that's the idea that we're actually pulling here if we use our modern geometry. I don't think that they're necessarily wanting me to use anything that Thales had unless they give me some kind of hint in the problem. So, but I can use that and all of a sudden it's pretty straightforward, right? So I can write up the paragraph proof or 2-column proof or, huh? Flowchart proof?
No.
I don't come up with a flowchart proof. Oh my gosh. 2-column. Okay, so statement and reason. It's actually just going to be a couple of steps. So step number 1 is going to say that angle AEB, the measure of angle AEB is 180 degrees. That's what Miss Summer gave me. How do I know that? It was given, or we can call it the definition of a semicircle. We know that it was inscribed in the semicircle. I probably skipped a step there about ACB is inscribed in the semicircle. It's okay. Okay. And then what? I need measure of angle ACB is 1/2 of the measure of angle AEB, and that's this whatever inscribed angle property is. That's what I'm going to call it. And then what?
Then you do substitution.
Mhm.
1/2 of 180 measure.
Do a little substitution here. Measure of angle ACB is 1/2 of 180 degrees. And then, boom, ACB is 90 degrees. Thank you. And that's just some multiplication, right? That's like my reason there is arithmetic, basically. So we can use that, no worries. And then, therefore, ACB is right. And how do I know that? The definition of a right. Oops, right angle. There we go. Whew. Put me on the spot with some geometry, Miss Alexis. It's been, what, 4 months since I've done that.
Are we going to have to do proofs like this, or is it just going to be like proving the splitting identity, which we did in class?
Yeah, like more like proving the splitting identity or one of those identity type proofs that I give you. Yeah. This is more of one of those homeworky questions that I was mentioning that I expect you to be able to do this stuff. Okay. That's why we use the 301 class as a prereq for this class, because we know that you're going to see some geometry stuff in here, but I'm not going to ask you that on a test. It's way more complicated than what I would. And it's not even a complicated proof, but it's way more in depth and geometry based than what I would give you on a test. Good question though. Now you got that homework question, yay. Anything about the test? Anything at all? Viewer. Test is on Thursday, so when we come into class, we will be ready to go on the exam. You can bring a calculator if you want one. There are a few of those multiplying like in Egyptian problems and stuff like that. So make sure you can do that kind of stuff from the beginning of the class. Don't forget, we had Babylonians and Egyptian math. Make sure you can convert between base 60 and base 10 and all that kind of stuff. That we did way back when. It's been probably 2 months since we did that. So don't just take it for granted that you know how to do that. I'm sure you do, but do a couple of practice problems before Thursday to make sure you're ready to go with that. Because I guarantee you there will be some multiply like an Egyptian, divide like an Egyptian kind of problems and that kind of stuff. Unit fractions, absolutely. Y'all want to see one of those? Been a while. That's on the sample problems, right? Do y'all have anything? When I just make one up, it's always ugly. Don't make up problems on the spur of the moment in your math class unless you have to. So remember that there's 3 different methods that we used in class. Y'all have one, or I'm just gonna make it up? Let's see. Probably a little too.
The range number that came into my head is 5/32, but that's probably too chaotic.
Yeah. How about 5/6?
3 if you have to leave the thing.
What? I haven't changed a thing, Miss Maria. Yes, regular class time, Maria. I don't know what to tell you. I haven't touched a thing. It's showing up. You may need to log out and log back in again. I don't know what's going on with your Zoom. That's funny. Sum of unit fractions. That's her heart. All right. Remember, there are 3 methods. That's her little heart. So you can use the 2/n table, and these are the ones that we're calling by name. There are other techniques you might use, right? But you can use the 2/n table. You can use Fibonacci's method, and we can use the splitting identity. Can you see now, Miss Maria? That's okay. You're welcome. Yeah, those 3 different techniques. So make sure you know the difference between them. Do y'all want to see one in particular? Okay, Fibonacci method. No worries. By the way, in my head, I'm thinking to myself, I wouldn't do any of those. Because I just looked at this and went, hey, look, 2/6 and 3/6.
Yeah.
Right? 2/6 will reduce nicely to 1/3 and 3/6 1/2, and I'm done, right? So if you see something like that, then hopefully the one on the test won't be that simple. But I would just split it like that and be done. But yeah. Fibonacci method. How does that one go? Pull out the subtract the largest unit fraction possible. That's what I'm after. So we want to take 5, 6 and figure out what's the largest unit fraction. I always do it as scratch work off to the side. How did I do that again? Do the reciprocal. So 6 over 5. And we want to sandwich him, right? What's the whole number that's smaller than him? 1 is smaller than 6/5, which is 1 1/5, right? And 6/5 is less than 2. So find the two whole numbers, or natural numbers, or however you think. Thank you, Maria. Those will fit in between. And now flip it all back over, right? So that just gives me a reference point, but I really want to deal with the 5, 6 guy. So this will be 1/2, and this will be 1 over 1, or just 1. And what's the big thing you have to remember? When you flip it back over, you flip the signs, right? So 1/2 is less than 5, 6. That means I can pull 1/2 out, right? That's good. And 5, 6 is less than 1. It's not actually true. 1 is greater. Okay, have to think about that one. It's because it's a whole number. It threw us out, maybe. Doesn't matter. We want the 1/2 to be less than, and it is. So we're good there. Flip the signs, I heard. Good. Okay, so we're going to pull the 1/2 out. Oh, it is less than 1. What is wrong with me? Yeah, I was looking at this number and comparing. Okay, 5, 6 is less than 1. We're good. Okay. 5, 6 minus 1/2. There we go. Subtract the largest possible unit fraction. That's what we wanted to do. So we pull that guy out. I need a common denominator. Oops, 3, 6. So that gives me a 2, 6 left over. And fortunately for us, that will reduce. And we are done. Okay. Sometimes people forget to pull that when they go back and do their sum of the unit fractions, they forget that they pulled out this 1/2, especially if they had to do it 2 or 3 times, they might lose one of them. So maybe box them off or something to make sure that you don't lose anything. 5, 6 is equal to the sum of 1/2 plus 1/3. Done. And you're not finished with these problems until you write them as a sum of unit fractions, right? So just because you found the 1/2 and the 1/3, yay for you. But if you don't come back and decompose it and write 5, 6 equals 1/2 plus 1/3, you're not going to get completely full credit. Thank you, Maria, for confirming for me. I'm so sorry. 5, 6 is less than 1. I don't know.
Are you going to ask us to use specific methods, like use this minus 2 over table?
Yeah. And what I actually normally do on a test, I haven't written it yet, but what I normally do on this test is I'll use the same fraction over and over again. So if you happen to have the same thing, like this was 1/2 and this was 1/3, and then on, when we did the splitting identity, maybe you got a 1/2 and 1/3, but on the third method, you get something totally different. It doesn't mean that your third answer is wrong, right? It just means that you need to make sure that that's equivalent to what you started with. Yeah. Because remember, these decomposing unit fractions part is the one that really gets kind of carried away. You can go down a rabbit hole. Maria says, will you tell us which decomposing method you want? Yes, it'll be on that question. So like if I was using 5, 6, it would say number 3. Part A, decompose 5, 6 as the sum of unit fractions using the 2 over n table. Part B, decompose 5, 6 and the sum of unit fractions using splitting identity. Part C. So I will tell you the same fraction over and over and over again. Yep, different methods. Absolutely. Y'all remember this? It's been a while. We did those. Go back and brush those up a little bit. So, yes, regular class time. We will come in, we will take our tests, and we will go, go, go. And if you're not in Commerce, like Christina's in Mesquite, you've already made arrangements with me for your test. That's great. If you have not made arrangements with me for your test yet, then I believe I gave you through today on D2L to make those arrangements to make sure I have a test for you. Like somebody's coming to the testing center instead of coming into class, and that's fine. So, yay. Otherwise, I assume you're going to be right here in Commerce with me in class. Thank you, Maria. All right, y'all done? It's 3 o'clock. We've been at it for close to an hour. You don't have other questions? I don't have anything. What you got?
This is totally unrelated. You know what the writing center is?
The
The writing center?
It's
in the bottom of the language, all the languages next to the journal.
you know where Binion is?
Yes.
It's on that side of
Okay.
campus.
So,
It's
right outside this building, there is like a university map.
ooh.
It says like Talbot Hall, I think now. Or
Yeah.
Talbot Hall of
Yeah.
Languages.
Okay.
Yeah.
Thank you.
You on the wrong side of campus for that. No, I'm kidding. It's a lovely day to walk across campus, so good deal. I walked. All right. Well, if y'all don't have anything, then I'm done. Have a great day. Stick around if you have questions.
I think I messed up.
Like a what?
I think I messed up with algebra.
Pause the recording.